This is Sun Devil Orbital Systems presenting Lantern, the Lunar Autonomous Navigation and Timing Relay Network. Lantern will support future Artemis missions to the Moon, specifically the Southern Pole, by allowing the crew, autonomous rovers, and other habitation needs to be able to communicate and gain navigational data via the Lantern system architecture. This Lantern system architecture will support the crew by allowing for communication systems to have extended periods of communication periods over the southern pole with a high eccentric elliptical orbit. The current lunar navigation is mission-specific, temporary, Earth-dependent. This makes it hard for current crews to be able to communicate long-term with Earth. The opportunity for Lantern is that Artemis missions require safer navigation, tracking, and landing support, along with communication continuity to allow further communication for long-duration missions. The local network reduces reliance on direct-to-Earth visibility and allows for persistent infrastructure supporting multiple users. Lantern creates a scalable architecture for Moon to Mars operations in the further future. Our proposed solutions uses reverse ephemeris to use position from satellite orbital data and Doppler range rate measurements to calculate navigational data in sub-millimeter accuracy. This will also allow for a constellation network to provide communication for multiple users at a rate that exceeds the current rate in megabits per second from Earth to the Moon.
Lantern's mechanical solution focuses on designing a satellite that provides the necessary capabilities for satellite operation. Aluminum 6061 T6 is used for its strong structural support and extensive flight heritage. Going style deployment is utilized to reduce the forces upon deployment and to maximize the total surface area. In order to keep the mass low and the volume within the 3U chassis, all the necessary components are used only for critical systems. This includes the onboard computer, attitude determination and control system, electrical power system, battery board, and transmitter. Aluminized Kapton multi-layer insulation is utilized in a 1 millimeter thick coating within the chassis to keep all components within thermal regulations.
To validate our decisions, a transient thermal analysis was conducted in ANSYS. Both hot and cold orbital cases were considered, and external heat loads were applied to simulate the solar radiation, the lunar albedo, and the lunar infrared emission. For the values of solar radiation, they were calculated by multiplying the solar absorptivity of each component by the solar radiance. For lunar albedo, the same equation was used, but multiplied by 12%, since that is the heat flux reflected by the moon. For the lunar infrared emission, the emissivity of each component was multiplied by the IR emission of the moon. The components were modeled with a radiation heat loss to an ambient temperature of 3 Kelvin to simulate deep space conditions. All components were modeled with internal heat generation, and we found that the lowest temperature for the components was negative 2.3 Celsius, and the highest was 45.5 Celsius. This falls within the operating range for the components, which is good.
For Lantern's recovery and redundancy plan, we include battery capacity, power generation, and EPS distribution. For the battery capacity, we include one additional battery to maximize the amount of storage we can get on the satellite if one fails. For the power generation, we include double-sided solar panels so we can maximize power generation from the light side of the moon when the sunlight is reflected. For the EPS distribution, we use cycling of the EPS to maximize the amount of power that goes to individual components based off which ones are on or off for the cycle that we are using at that certain time. This includes independent power channels and subsystem level fault isolation. The subsystem level fault isolation allows for each component to be turned on or off depending on whether or not it's needed at that current moment.
Each Lantern satellite is expected to cost $75,000 per. This would mean that the entire Lantern constellation is approximated around $1.35 million. Component lead times based on the current component availability on the market is approximated to be between 9 and 12 months. The entire assembly is expected to take 36 weeks in duration. The entire mission timeline would total to 2 years in length.
The system architecture for Lantern includes 4 polar frozen elliptical orbit layers for southern pole persistence. This allows for 3 concrete satellites to be orbiting in a polar frozen elliptical orbit at any one time. The 4th redundant satellite will only be in use if one of these 3 fails. There is an optional distant retrograde orbit node for timing backup and Earth relays assistance. This is optional because it's technically not needed with our constellation. The surface micro relay mesh supports cratered or blocked regions on the southern pole. This involves terrain masking, whether it be filtering from the dust, or if the antennas are blocked by some sort of radiation. These micro relay mesh will support Artemis missions to the southern pole. The ground stations at the habitat will provide external updates, telemetry, and network health monitoring. This will allow for the constellation to constantly be monitored by Earth telemetry sites and lunar-based nodes. The orbit navigation and orbit design. The primary navigation layer uses polar elliptical orbits. As you can see, the blue lines represent the polar elliptical orbits used, with RAN indications being that the polar orbits aren't exactly directly over the southern pole. This is so that we can cover a wider range of angles that are appropriate for the horizon. This will help terrain masking, this will help shadowing, and this will ultimately help the amount of area affected by the constellation system. The target orbit concept is approximately 50 to 100 kilometers on a paraloon, with a 250 kilometer apoloon. The 250 kilometer apoloon will maximize the amount of time that we spend over the southern pole. The offset RAN and satellite spacing improve simultaneous visibility over the southern pole. As said previously, this will not only add redundancy to the southern pole triangulation, but it will also allow for the satellites to increase the wide range of possibilities for exploration on the southern half of the moon. Horizon to horizon visibility, windows support recurring communication, and also allowing for more communication to be done by satellites in previous constellations, as the angle between them will be 20 degrees or less. This allows for the entire constellation, plus other pairs of satellites, to be used for increased sub-millimeter accuracy for navigational systems along the moon's surface. The core technical innovation in this is that the orbital constellation uses reverse ephemeris from a single link navigation method into a networked lunar infrastructure. This is important because this allows for a wider range of connectivity along the lunar surface. Multi-satellite simultaneous solutions reduce two-point ambiguity between satellites, allowing for us to not only gain sub-millimeter accuracy on the navigational ground stations, but also it allows for multiple users to stay connected at once, communicate between each other, and communicate telemetry back to Earth. Not only does this help that, but it also integrates Doppler range rate measurements to support position and velocity estimation on the orbital elements, along with the ground stations and ground elements. This could include autonomous rovers, astronauts, habitations, or other ground assets that are very important. The regenerative relay also allows satellites to decode, prioritize, and retransmit critical packets. This uses the rad-hardened onboard computer system to allow for us to use overhead bits to allow for a certain amount of error that happens between communication between satellites. When the radiation hits the satellite, there will be some sort of error that maximizes in the communication between the satellites for the data relay. To maximize the amount of data that we are able to send between satellites, we include this overhead bit size so that we can include the error, and eventually each packet sent will be the correct amount of packets received by each satellite. The future of Lantern. For the impact, Lantern will provide not only persistent navigation, timing, and relay infrastructure for lunar surface operations, but it will also improve crew safety through astronaut tracking, rover support, landing support, and emergency communications. This is critical for future Artemis missions to the moon, eventually also to Mars. As seen on the last bullet point, we can also extend this to Mars, Europa, and other planetary exploration environments. Because Lantern is so cheap, it can be used, reused, and reused over again for other missions. For the next steps, we conclude that Lantern will be able to be used for a cover simulation of all orbital adjustments. This will also include link budget validation, navigation filter testing, and component procurement plans. We want to patent Lantern, and the commercialization research will be used to make sure that Lantern will be able to make money on the missions that Artemis will be sending to the moon rather than just taking money. This also comes at a price because we will be using components that will maximize the efficiency of the Lantern plan, but also will be cheap enough to be a viable option for NASA in the future years. We want to thank you for listening to this presentation on Lantern, the Lunar Autonomous Navigation Timing Relay Network by the Sun Devil Orbital Systems team.